Folks, welcome to our compilers class. Again, we'll start with a couple of announcements and then we'll get back into our topics. So, as you know, we don't have midterm mainly because of the remote teaching, and it's very difficult to administer it using some softwares. They're there, honor lock and all that. But instead, from last year when we had to again do it this way, we decided to, instead of having a midterm, have a term paper. So I've gone ahead and assigned the term paper, which is roughly given about 4 weeks. Please get started on it. It's due in the very beginning of April. Mainly, it builds on our knowledge of PRE, which is the advanced data flow analysis that we have seen. And hopefully through the homework, you have a very clear idea of the PRE working in terms of the different computations, earliest, why do we compute that way? There's those sets. Then later in, we lower it all the way till we either meet a basic block where there is a need to cover an expression, or then we keep sinking till the point of we don't want to come in the path of availability and so on. So the understanding of PRE, I hope, is thorough. And now, of course, this paper builds on the next step, a very solid paper and a very well-known paper, CompRE. And then there is a small side paper that we are also going to use for the term paper. So I want you to kind of first read and understand the core concepts of these papers and then read the questions, which will guide you to reread the paper and understand some of these things which are asked in the term paper, and then develop your own examples, develop your own understanding of the concepts and write it in your own way, the way you understood it, using your own examples, your own writing, your own illustrations. Answer each one of these questions. They're not hard. They mainly are based, of course, on all the content which is already in the papers, but you will have to understand it and write in your way. So that's the exercise. So please get started and develop it over a period of time. That's the intent here. And don't keep it at the last minute. And similarly about the project also, develop it over a period of time. You have, of course, the term paper is individual, but you can ask clarification questions on Piazza and even discuss with each other. There's no problem about that. Of course, all your answers should be your own. Of course, the project is a team exercise. And so you can work with your project partner and come up with a solution strategy and a plan. And again, develop it over a period of time, which will help to mitigate any last minute issues and problems and so on that you may run into. So don't, again, this is not a class where you want to play with, hey, I can just finish it in the last 2 weeks or last 1 week. Or even worse, I have seen, not in this class, but in the undergraduate class, students think this is yet another piece of software and they can hack it out in 5 days or 4 days or 3 days. Absolutely not. You are setting up yourself for an utter failure by not doing it and spreading it. There is a reason why we give this much time. Of course, one intention is to adjust with your schedules, but more importantly, you must design it, plan it, and then slowly get rid of the bugs or whatever issues you're facing, and that takes time. So That's basically the announcement. So we'll get started on the SSA, and that's what we'll get going with. Um, so let me illustrate the core concept of SSA as we were talking, and then we'll get back and develop some of the necessary equations and algorithms and so on to be able to generate the minimal SSA. That is our intent, because as you will see later, any SSA based optimizations ask you to walk through the inserted phi functions and so on. So we don't want these phi functions to be inserted unless they're absolutely necessary. They're bringing two different definitions together. If we have a phi function which are bringing the same definition and merging, then I think the size of SSA will become large. That is one concern. And the second thing is, when you do optimizations, you will be unnecessarily traversing through those functions wherein the definition has not really changed. So going back to our favorite examples, which we are going to use through and through of through the discussion mostly. So this is a diamond graph, which is very standard, which is used in almost all our discussions. And so what we were doing was, with regard to this particular graph, we had some definition here of a particular variable. Let's call this as A1. And this is in basic block B1. And with regard to this, each definition one at a time. First job, which was important for us to insert the phi functions with regard to this variable, so that its definition must be gated with regard to some other definition. What the other definition is, we don't know. We'll come up with the populating the phi function in the second step. But first is to just insert a phi function for a given variable. And so what we said last time was this, that this particular variable is prevalent in its area of domination, where it is supposed to exist just by itself, such as even these two basic blocks here, B1 and let's say this is B4. These are B2 and B3. We have B2, B3, and this is a B4. You can see that this whole area of B1, B2, B3, B4 is dominated by this basic block B1. In other words, whenever we enter any of these blocks, we must come via B1, as you can see. And so we'll hit this definition of A, which is A1 there. And that's the definition which will be prevalent in this particular block as far as A1 is concerned. So as far as A1 is concerned, there is no need to insert any phi function in any of this region. But the moment we get out of this region of domination of B1, which contains this definition A1, such as, let's look at this block, which is B5. Here is where we must insert a phi function with regard to this variable A. So one of the definitions will come from here. The other definitions, because we can enter this particular block from the left-hand side as shown by this big arrow, we could come in here with a totally different definition other than A1, because it's not dominated. B5 is not dominated by B1, as you can see here. And so B5 can get a definition which is other than A1, and we'll get it if we come via the other edge here. This is which is marked currently. And so therefore we must insert this phi function here. So this is the strategy which we follow to decide where we must insert the phi function with regard to a definition. And since this is a minimal sort of insertion that we must insert it, there's no other alternative. We are definitely guaranteed that there will be a different definition prevalent there. The whole IR is minimal. So in other words, as you can see here with regard to this function or with regard to this block B4, we don't insert any phi function because it's still dominated by this particular variable. So each variable decides where it must insert a function, and that's why this form is minimal. And if we do it for each one of the variables, then we'll be generating the minimal SSA. By the way, just to give you a very good idea, I have put two resources on there. One is, of course, our slides, which we are going to use for SSA discussions, which I will be presenting. But other than that, one important thing that you should read is the Muchnik's SSA handout, which is also put there. And then those who want to go a little beyond that, the original SSA generation paper is also there, but Muchnik covers it pretty adequately. So you may want to refer to papers only for some more details and things. The Muchnik's handout is good, but don't just rely on slides. Do read the Muchnik handout. So each variable therefore gets its own phi function, and that's what we keep doing. And if we, for example, go to some other variable such as this, let's say A2 here in B3, then what will happen is there will be a gating function here with regard to an A, and two gatings will be attempted. First of all, one is because of this B1, because this particular block, B6, is not dominated by B1, so it will go ahead and insert the function. And then when we go to B3 also, B3 also does not dominate B6. So it would see that, okay, there is a need for a function with regard to A, and it is already there. So it will not insert a second function. So in other words, for a given variable, we don't insert two functions like these. We insert only one. In whichever order we process them, it doesn't matter. We could have put here a phi function with regard to A variable using B3, and in which case B1 will be superfluous and it will not insert its own function. If we have, of course, a need sometimes to have a function with regard to different variable, of course that is put. So let's change this example, and maybe we have a B1 here, not A1, but B1 in small b1 in big B1 basic block. So in this particular case, we will put a phi of B as well in this particular B6 because of this B1 coming from here. So this is my B1, and it will insert a phi of B in this particular basic block here. And then B3 will insert a phi of A here, and so on. And that will have phi of A and phi of B with regard to these two different variables. The idea is, of course, all A variables, they generate different definitions of A, and then some of them definitions merge at a particular point, and there will be a gating function with regard to phi of A. And similarly, for some other variable B, there will be gating function with regard to phi of B, and so on. So that's how this process will work. And we'll generate these gating functions. As I said some time back, sometimes it could be that at a given basic block, there could be multiple trying of insertions of phi functions, such as phi of A might be tried twice, but we'll of course keep one, and then in the renaming step, it will get populated appropriately, as we'll see later. The one which is reaching definition there to that gating function will be the prevalent one. So if we had phi of A here, A1 here, and A2 here, you can see that this phi of A here will actually, of course, have A2 in it and not A1 because that's the definition. And in the renaming step, we'll take care of that appropriately. The other definition will come from the other edge, whatever that is, and it will populate this phi of these functions. But the first step in the SSA generation is just insertion of gating function for each of the variables. And once we do that, then the second step will be how to populate those with the actual SSA names and generate those names and so on. So that's what is going on. Now, are there any questions at this point about generation of these phi functions or insertion? If there aren't, we will then look at a little bit more formal mechanisms of how these functions are really decided in terms of where to insert them. So let me ask if there's any particular doubt or any question. You can see that they're all present just on the outskirts of the dominated region. This is the dominated region of, you can see that this is a region of domination for A1. And then the moment we encounter a basic block, which is right on the outskirts of that, which is not really dominated by that particular basic block, but which is right on the outskirts, that is where we need to insert the phi function because that's where the other definition will meet the current definition. So if there are any questions, we can take them now, or then we'll get into how to find these different basic blocks where we should really insert the phi functions. Okay, so, and if there are any questions, I'll of course be happy to entertain later. So let's kind of move forward and see how this particular insertion really works in terms of determination of the points. So as you can see here, the way we are doing it is we have a definition of A1, let's say in a given basic block P1. And our interest is in really finding out all the gating functions that are a must for this definition. So we are working off in a definition by definition manner. So fortunately, you can see that if we do it definition by definition, then the size of the program, if it is n, this particular algorithm will be a function of that. But you will see that we are really looking at the basic block which contains this particular definition, and that really decides where we are going to insert the phi function. So in short, the complexity of this particular algorithm first will be to map a given definition to a basic block, and that will be order n, because we quickly find out where that for each definition, which is the block. But from there, the decision about finding the where this definition, this gating function will occur, this phi function will occur, will be proportionate to the number of basic blocks. So let's call those as n. Small n is the number of basic block, will be proportional to the function of n. Of course, the amount of work that will be done with regard to each basic block will really decide whether this is n cube or n square or n to the power 5 or n to the power 7, or if it's exponential. But it is a function of n, not really bigger n. So that's the first point I want to make. The second point is let's now look at what is the mechanics of generating these functions. So we know that this is a sort of, I'm sketching it here in a little abstract way. This is a region of domination for this particular basic block. And what we are trying to do here is kind of finding out such basic blocks here, which are like B2 and B3. And these basic blocks are really what we are interested in, which are really on the outskirts of region of domination. So if you carefully look at it, the way we can characterize these basic blocks is that let's consider B3, for example. And we can see that, first of all, there are two observations which are in place here. Let's call this as, let's say, generally a basic block B4, and let's call this as B5. Okay, so which is the predecessor of this B3 in the region of domination. Of course, the predecessor of B3s could be several, like for example, this block could also be a predecessor, and this also could be a predecessor, but that's not the point. The point is this, that I'm interested in such a B3 whose predecessor is dominated by me, okay? But the block itself is not dominated by me. So we can think of taking all the blocks, first of all, which are dominated by B1, and finding out their successors, which are not dominated by me. So that tells us that one of the two things, B1 dominates B4. That's one relationship. And the second relationship is B1 does not dominate B3. Okay, so these are the two key relationships which we are interested in. That B1 dominates B4. Okay, B1 dominates B4, and B1 does not dominate B3, which is a successor of B4. And similarly, you can say the same thing, that B1 dominates B5 here, and then successor of B5, however, B2 is not dominated by B1. So what we could do is we could look at all the nodes which are dominated by B1, look at their successors, and then pick only those successors which are not dominated by me, by that B1, and that will give us a way of finding out the places where we could insert these phi functions with regard to the definitions that sit in B1. So it could be one definition A1, it could also be maybe some other definition B1 here, or C1. All of them will be all covered by the same logic. We will map them to the B1. First, basically, we'll find out all the nodes which are dominated by B1, and then each one will take and we'll find its successor, and we will choose only those successors which are not dominated by B1. Okay. So in this process, what will happen is, let's say if we have nodes here which are dominated by some successors, like the way we saw this diamond graph earlier, which are dominated by B1, like what I have just sketched here, is something like B6 here. So it's the successor of B4, but that is also dominated by B1, so they will not be selected for dominance frontier because they are still within the dominated region. So B6 is not selected because although it's a successor of a node which I dominate, which B1 dominates, it is still dominated by me. I'm looking for one which I do not dominate, such as B3 and B2. So they will be picked, but B6 will be rejected out of these. So that's basically what we are interested in, and such nodes are called as dominance frontier of this particular basic block B1. So what is the dominance frontier of a given basic block? It is that node whose predecessor I dominate, but I do not dominate that particular node itself. So now this is the way the phi functions will be decided in terms of their placement. And there is this one slight wrinkle which we'll tackle in terms of the definition of this dominance frontier to make it more generalized to a case which I'm just going to show here. So most of the cases will fall like this. What I will do is I'll take a node, I'll find out all the nodes which I dominate. I'll start with one by one in this list of these nodes which I dominate. I'll take their successors and I will find out those successors which I do not dominate because the control can come via other path into them, and therefore that can bring another definition. And those will be my placement for all the definitions within me. Me means the basic block, and I will place all the gating functions with regard to all the definitions which we have, such as phi of A, phi of B, phi of C, all the different variables which are over there. I'll place the definitions with regard to them. And that will cover what is called as the dominance frontier of B, all these cases. Now, take a look at this particular case and let us see how to tackle this. So what is going on here is this, that let's say some definition, again, A arises over here in this block. Now, if you really apply this particular definition, we want to find, first of all, the nodes which are dominated by me, which include, first of all, B1 dominates itself. So I start with B1. But then what I want to find out is their successors, which are not dominated by me. So here you can see the successor, because it's a self edge on a loop. The successor of B1 is B1 itself. Okay. And I dominate that. So there will not be any phi function placed here as per definition of dominators, frontiers. So which is not acceptable, because you can see that some definition is coming here, say 0, let's say. This A1 is going back here, and there is a need for phi function here. So this is a corner case which is not really covered by our current definition of dominance frontier. So how to extend our current definition? Well, there is a simple extension, okay, which is instead of saying that B1 does not dominate B3, okay, we will simply say that that successor is not strictly dominated by myself. So if I have a B1 and if I have one node B1 and B and B dash, I will have a dominance frontier at B dash. I will have a dominance frontier at B dash, provided I do not strictly dominate B dash. What does it mean? So this predicate, not strictly dominate another node, really can evaluate to two possibilities. One is I do not dominate that node, so B1 does not dominate B dash. That is one possibility which we covered here. That means there is another part to that which can avoid coming via this B and so on. Or the other possibility is this, that we can say that B1 dominates B dash, but it's not a strict case of domination. In other words, it is okay to have this domination relationship provided B is equal to B dash. So this case, the second case of self-domination, is okay here in terms of the phi function placement. What it says is this successor, whatever you are talking about, could be dominated by the original node B, provided it happens to be itself. But for all other cases, when B is not equal to B dash, we must not dominate it. Okay. So that is what is the implication of this definition. that when B is equal to B dash, it is okay to have a domination there. I could dominate it, and that would still allow a phi function placement there. But if B is not equal to B dash, if we are talking about a different node, then it must be that we should not be dominating it in this particular case. Like B3 is not same as B1. And so for dominance frontier to exist here, B3 and B1 must be distinct. The other possibility is this, that I dominate a predecessor of that node in the dominated region, and the successor is myself, and I dominate it because of the self-domination rule, and therefore the predicate is not strictly dominate. Okay, that means self-domination is okay. And so this particular one which covers this case, you can see that if we take a successor of B1 here, it happens to be B1, okay, and then we can examine whether this predicate is satisfied. B1 dominates itself, and of course B1 is equal to B1, and so therefore this will be a phi function candidate over here. Now, not only for this particular case, but for any loop which is a back edge, this particular relationship is true, as you can see here, because even if you have some region here which this dominates, B1 dominates, and this back dominates from here, as in our loops, you can see that finally all this region will be because of the definition of loop by B1. And let's say this will be origination block which goes back to B1, and if you take a successor of that node which is dominated by B1, it will be this again B1, and B1 will dominate itself. We will satisfy this particular definition, and therefore we will include this in the phi function. So for all loops to cover their back edge cases, we must extend the role of non-domination to non-strict domination. In other words, this could have two possibilities. One is, of course, non-domination when the nodes are distinct. And the other possibility is it could also allow a self-domination, which is a negation of strict domination when the nodes are the same. And so that covers all the different cases, such as these acyclic cases, what you have shown, and the cyclic case in terms of a loop, back edge, and the entrance, the phi function sitting at the entrance of the loop itself. So now we have a complete definition. So what is the complete definition? Complete definition is what is the dominance frontier of a given block. That is where we are going to insert the phi function. Dominance frontier consists of all blocks of which are satisfying this relation. They are successor of some node which I dominate, and that successor is not strictly dominated by me. In other words, either I do not dominate it, like in these cases, B2, B3, and so on, or if I dominate, then it must be self-domination. It must be that the node is myself, and both are included in the dominance frontier of the basic block. And all the definitions within that block, therefore, will find their respective phi functions to be placed into the dominance frontier of that block. So that's basic equations which govern these. And then how to find it is yet another story. That's what we'll get to. But I hope the concept here and why it is important to find on a basic block by basic block basis is clear. First of all, it reduces the complexity from having to find it for every definition to every basic block, and use the basic block's dominance frontier as the one for the definitions which are within it. More specifically, downward exposed definitions are the ones which are really going to participate in this dominance frontier. They will be the ones which will be potentially gated. So that brings the reduction from order n, which is the size of the program, to some function of n. And we will then try to find the dominance frontier for that block using this definition of non-strict domination of a node or a basic block, whereas the predecessor dominated by the basic block itself, and we'll use that to find the dominators for all the blocks. So the way this algorithm will work is we'll take each basic block, we'll find its dominance frontier, we'll find out the phi functions for the respective definitions in that block. And then, of course, this generates a new definition point. And let's say in this B3, you can see that there's a new definition point for A. Maybe let's call it A5. Now this A5 flows somewhere and again meets some other definition. So we must find the A5's dominance frontier and place another phi function there and continue this process and iterate on it till we do not insert any more phi functions. And that's why this is what we call as iterative dominance frontier. So in short, the SSA inserts phi functions. Those generate new birth points of the birth points of those variables. They in turn go around and meet other definitions of that variable and generate yet another set of phi functions. And this process iterates, and that's when at termination we would have covered all the phi functions which are needed for joining the different definitions. What are the definitions which are participating in phi functions? They could be native definitions like this A1, B1, C1, like that. And so they could participate in the phi functions, but they could also include the generated new definition, SSA generated definitions like A5, which will flow from there and which will join some other phi function. And that's how we'll iterate and include all of them. So this can take some amount of time because you can see that worst case we are finding out, of course, all the dominance frontiers for each one of the basic blocks, and that process can be a little tedious if we do not do it efficiently. And our goal is again to keep this process very, very efficient because of the size of IR, and typically we want to restrict it to linear process, which will be nicely covering all the dominance frontiers that we really need to use. So the second question is, how do we keep this f of n linear in terms of the number of basic blocks, and how do we generate it systematically so that we don't face a very high complexity in terms of doing some unnecessary work, and that's the topic which we'll take up now. But before we get into that, are there any questions, dominance frontier in particular, about non-strict domination special case that we have looked at here, and in general about dominance frontier, how it is, why it is first of all defined this way, and how it is computed, etc. If there are any questions, we'll take those, and otherwise we'll move forward to the computation of dominance frontier from these definitions. Any questions in the chat, Nathan?
No, nothing about the dominance frontier.
Okay. And by the way, this nice discussion you should read from the Ch1 handout, which I have put in. And the details of all that is in the paper, but Ch1 handout, which is a book chapter from there, will give you a very nice, clean definition and some illustration of these dominance frontiers, how they look, which should be very clear from this discussion, that which is pretty intuitive. Okay, so now let's get into the discussion of how to really compute these dominance frontier. And for that, we are going to make use of some very interesting observations. So again, we'll go back to our diamond graph. I did not want to reuse that because it was a little cluttered. So I'm redrawing it again here. And this is what we'll be again using to compute the dominance frontiers of these blocks. So what we do is we make use of some very simple observations and then use them to really use the dominance computation done for a set of blocks for the dominance computation for the block which dominates them. So let us focus on this block in particular, which is B3. You can see that this is a block. Let's say that we are interested in finding its dominance frontier. So you can see that this block in particular, in this particular case, does not dominate any block except itself, of course. So if you look at the dominance frontier of this particular B3, you can see that it will be this B6 and this B4. Okay. How do we find that out? We can find that out using a very simple mechanism. We look at the all the blocks which are neighbors of this block, which are successors of this block, and see if we can reason about whether we dominate those or not. So if you look at B3's first successor, that is B6, I do not dominate it, and therefore that's part of my dominance frontier. Because you can see that either we go through a whole bunch of blocks and then from there we go into some region of domination, or sometimes we hit the region of domination right away, dominance frontier right away, because the region of domination really ends here. You can see that B3's region of domination ends within itself and doesn't extend beyond it. So what we do in cases of each block is we find what is the local dominance frontier of that particular block. So local dominance frontier of what we call as DF local of each block, we simply look at its successor and find out if it is in it belongs to the region of dominance frontier or not. So in case of B3, we will look at its successor B6. It is not dominated, it satisfies this definition of dominance frontier. We'll include this into this particular set. Similarly for B3, we'll look at B4, which is where the region of my domination is just ended here. So I look at my successor, and that certainly is satisfies the definition of dominance frontier. And so even B4 will be included as well here. So we'll have B4 and B6 included in the DF frontier for B3. Now there is nothing else to this as far as B3 is concerned, because we have covered all the nodes which lie right out in the outskirts of the region of domination. So how can we say this? We can say this because B3 does not dominate any other block, and B3 dominates itself, and therefore any dominance frontier that we can look at is right on the outskirts of B3, which means the successors of B3 will be checked for dominance frontiers, and they'll be included provided I'm not dominating them. Similarly, if we look at B4, B4 dominates itself, there is no other node it dominates. So its region of domination ends here. And again, if we look at its successors, there are none here. And so the dominance frontier for B4 is phi, null. There is nothing in that dominance frontier. If we go to B2 and apply this logic, that let's see where its dominated region ends. It ends by itself. So therefore, it suffices to simply exist to go to its successor and find out if that should be in the dominance frontier or not. By again applying the definition that successor should not be dominated by me, and that definition is satisfied. So B2's dominance frontier again consists here of B4. Okay, so I hope you're following this logic so far. B3's dominance frontier had two parts, B4 and B6. B4 and B6. And this one, B2 had B4, and B4's dominance frontier had none, because again, there was no successor and there was no these things to be included there. Now, let's come to B1. B1 will try to apply the same definition in terms of what is going on. We will try to go to its successor and find out if I dominate or not, to find out its local region. So in this particular case, B1's successor, you can see that there are two of those, B2 and B3. But when we apply the dominance frontier definition to them, both of those successors are dominated by me. So therefore, the local dominance frontier of B1 happens to be null in this example. In some cases, there could be maybe a third branch, and there could be some successor which may not be dominated by B1. And so in general, there could be somebody there which is coming out of my local dominance frontier, because my successor is not dominated by me, and it could be possible that that is included in my local dominance computation. But in this case, my local dominance computations comes out nil, because what I do is when I go to my successors, each one of them is dominated by me, and therefore they cannot be included in the dominance frontier. Now, once we have the local dominance frontier computed, the question is, how do we find out the complete dominance frontier of a given node? Now, for that particular matter, you can see that the other dominance frontiers like B3, B4, B2, they're all complete. They don't have any other possibility, because their dominated regions end right there. And so whatever is in the local dominance frontier are their dominance frontiers. But that's not the case for B1. B1's dominated region is all of these, B2, B3, and B4. And so we must then therefore look for, as far as the B1's dominance frontier is concerned, again applying our definition, what is there on the dominance frontier of the nodes which I have dominated, and check if I should include those or not. So for that purpose, what I do is I compute what is called as NDF, non-local dominance frontier of B1. How do I compute that? So for that purpose, what I do is I go to each one of the blocks which I have dominated, which is B2, B3, and B4, one by one. I find out if the dominance frontier, the nodes which are in their dominance frontier should be included in my dominance frontier or not. Because what you can imagine is this, that the control can go from B1 to any one of these nodes which it dominates. And from there, the control can escape outside to a dominance frontier, as we have been seeing the definition of dominance frontier earlier. That's the mechanism of the way the control goes to the dominance frontier nodes. So therefore, what I do is I go to each one of these nodes which I dominate, that is B dominates, and find out their dominance frontiers and see if I should include those in my own dominance frontier or not, in terms of the dominance frontier computation, because the control could have escaped through them. So for example, here I go to a node which I dominate, like B3, and I examine its dominance frontier. Now it has two components. One of them is B4 and second is B6. Okay, so these are the two which I consider. Now you can see that B4 is still dominated by me, that is by B1. So I will not include that in my non-local dominance frontier because it is still dominated, and so therefore it doesn't conform to the dominance frontier definition. However, you can see that B6, as far as it is concerned, it's in the non-local dominance frontier of B1. Why? Because B6 is not dominated by B1. Although B4 is dominated and therefore cannot be included, what I'm doing is I'm looking at the dominance frontier of a node which I dominate, like B3. And it has two pieces in it, B4 and B6. And I individually look at each one of them and check if I dominate those or not. If I dominate those, then obviously they are not in my dominance frontier, because for them to be in my dominance frontier, I should not be dominating them under the definition of dominance frontier. So that's why I reject B4 but include B6. And so non-local dominance frontier of B1 with regard to B3 will be B6. Okay. Similarly, I go to all the other nodes and see if their dominance frontiers and their components should be included. So next I go to B4. See, from B1, I'm going to my first node, which I dominated, B3, I'm sorry. B1 is dominating B3. So I checked that and I took the one which I do not dominate and included that, B6, in my dominance frontier. Next, I go to the second node which I dominated, B4, and examine its dominance frontier and see if there is anything there which I should include, which I do not dominate. So B4's dominance frontier is phi, so there is nothing to be taken from there, so we ignore that. Next, we go to B2, which is another node which is dominated by B1, and examine B2's dominance frontier, which happens to be B4, which we computed earlier as a local dominance frontier. So we can see that in this particular case, we should be examining B4, whether we should include B4 in B1's dominance frontier. And of course, the answer is no, because B4 is again dominated by B1, so it cannot be in B1's dominance frontier. And so that's why the non-local dominance frontier of B1 happens to only include B6, which is this node. Now, how about the local dominance frontier of B1? We already calculated that by going to its successors and finding out if they are to be included or not based on their characteristics. So each one of them were dominated by this B1, so that was null. And so the only dominance frontier of B1 here happens to be just this non-local one, which happens to be B6. So is this methodology clear in terms of how I am computing the dominance frontier of a given node? What I do is I split the computation in two parts, local and non-local. So the local part helps me if my region of domination ends with regard to my successor right there. And I include that by just checking whether my successor is to be included in the dominance frontier or not. If it's not to be included, because I'm dominating it, I do nothing. So I compute therefore the local dominance frontier of B1 in this case as phi. The non-local one is the one which escapes through one of the nodes that I dominate. So I go to all the nodes which I dominate, take a look at their dominance frontiers, and pick up those sets and include only those nodes out of those which I do not dominate. Like in this case, B4 and B6 were examined, but B4 both are in the dominance frontier of B3. B4 and B6 in the local dominance frontier, they were computed and they are there. However, B4 was not included in dominance frontier of B1 because B4 is dominated by B1 and B6 is not dominated, so it was included. And similarly, I did it with B4's dominance frontiers, which was null. B2's dominance frontier, we had one element B4, but that was dominated by me, so it was not included. And I took a union of all these, and that's my dominance frontier, which is non-local. And my local one was null because both of these other ones, there was no dominance frontier there to be included because of I dominated both. And so I just took my local and non-local and then took the union of these, and that became my dominance frontier. Any questions about this methodology? Because this is really at the heart of the algorithm, and I'll just from here illustrate the algorithm, how this algorithm really works. If there are any questions.
Buddy had a question on chat, but I wasn't sure if it was answered in your further explanation. Okay, cool. Yeah, no, we're good. Thank you.
We're good. Okay. You can always, of course, re-ask if you want. So basically, what is going on here is this. Let me now show this dominance frontier computation in a little different way in terms of how it really proceeds. If that explanation was clear, so I'm going to again to reduce the clutter, just start with a fresh drawing here, the same one, and so on. This was my B4, this was my B3, this was my B6, I believe, and so on, and then this was my B2 and B1. So let's look at the dominator tree here in terms of what is going on, and we will be using that for computing this dominator relationship. So B1, you can see that it dominates B2, B3, and B4. All of these. So the way I will do this particular computation is from bottom up. You can see that none of these nodes, B2, B3, and B4, dominate any other node. Okay, you can see it from this particular tree that they do not dominate any other node except themselves. So in short, the only component they will have because of this particular reason is that the moment they step outside themselves, they will be in a dominance frontier arena. So we will do purely local computation here, DF local. Okay, what is DF local of each one of these nodes? We go to their successors, and since we do not dominate them, because their region of dominance, each one of them ends right here. This ends here, this ends here, this ends here. We'll go to the successors, if any, and we'll compute their DF local dominator sets, which are examined through their respective edges. So we'll take this edge, and we'll find out, we'll include this particular B4 and B6 as their this dominance frontier, and those will be the only dominance frontiers that will exist. So for each node, we will be having what is called as DF of that node, dominance frontier of that node will have non-local dominance frontier, which will be coming out of the sets of nodes it dominates, union of all those as per the different nodes it dominates, and then there will be a DF local because of the nodes which are right outskirts of this particular thing. So in this case, as you can see, the DF of each one of those nodes at the leaf will be DF local only, because there is no other component to them. They do not dominate anybody. So we'll simply compute going to their successors and include, which I had done earlier. B2 will have again here B4 because right on the outskirts, and out of B4 we'll have null, which is zero contribution there. So bottom up will be going. So for leaf nodes, purely local computation. And then for a non-leaf node, we'll have two components. One is NDF and the second is DF local, right? So for this example, you can see that if we go to each one of the successors of B1, they will all be dominated. So if local will be null, okay, and non-local DF will come out of all of these which I dominate, these sets B2, B3, and B4, but with the condition that that element, in order to be present in my dominator the frontier, that node should not be dominated by me. So we'll start examining, and we'll go to B2. It's set B4 and reject that based on dominators relationship. I dominate B4. The other DF local which we have here is BF and B6. Again, we'll reject BF out of that. But the only one which will include out of NDF relationship through a node which I dominate will be B6, and that B6 will be imported here, and that will complete the dominator set computation for B1. And then similarly, if I keep going up the dominator tree, I will have all the dominated sets coming from the nodes which I dominate. I'll pick out of those the ones which I do not dominate the nodes and include only those, and then I will couple it with my DF local computation. Okay. So of course it's possible that in this particular case we also had some DF local for a particular example. In this case, it is just that it is P, but in general, we could have a DF local computation. And that's how I will keep going up. So I will make a use of dominator tree here, go bottom up, start with the leaf nodes, which have only DF local sets because they do not dominate anything. Compute those. Use those sets to move one level up to my immediate dominator. See, these are my B1 is an immediate dominator of B2, B3, and B4. So I will move only one level up, not multiple levels up. I will move to my immediate dominator, IDOM, okay, using this particular dominator tree. And I will give my sets to my immediate dominator. My immediate dominator will examine them, will only accept some of those elements which it does not dominate, like B6, and include it in its NDF. And it would have its own local set of DF local. Sometimes it could be null like this if it dominates each one of the successors. Other times it may not be so. If it, for example, does not dominate one of them, and it will include those, and because of that reason, once it includes those non-local, it will combine and it will generate its dominance frontier there, and similarly we'll keep moving up and up and up. That will allow me to do the dominance frontier computation. You can see here the total number of computations that are being generated is equal to the number of edges here on the dominance dominator tree. And you can see that in general, no edge of the graph is visited twice. In other words, if I'm examining an edge, it is either coming out of my dominator tree because of NDF relationships, or if I'm looking at a particular edge, it is coming simply out of my local dominance frontier relationship. And so no edge is examined twice. And the number of such edges, especially in the dominator frontier, dominator tree computation, is equal to n minus 1 because it's a tree. So n is the number of basic blocks, so the number of edges is n minus 1. And then the local ones, you can see that in general, it would be at most equal to all the neighboring edges, which will be there in the graph. The graphs tend to be very sparse. This could be at most order E, because the number of edges cannot be more than that for their successors and so on. And you will see that the split will be between these two, and because of the sparsity of graphs and so on, in practice, this really executes somewhat proportional to n, and so this is really order n in practice. It could go to n square, but it doesn't because of the sparsity of the graphs and so on, and this becomes very efficient computation. So again, how do we do it? Bottom up, in terms of starting with the dominance frontiers of all the leaf edges, which are pure, taking them, propagating them up to the immediate dominator. The immediate dominator removes certain nodes from them which are dominated and couples it with its own set of local frontiers. And this whole process keeps going, and finally we compute the dominance frontier at the loop. And we have covered here all the basic blocks, as you can see, because they participate in the dominator tree. Complexity in practice is roughly is very much near close to order n because of the sparsity of the graphs. Our graphs in our you can see that control flow graphs are really, you can see that sometimes there is a back edge which determines a loop, but we have only few back edges, and in the dominator computation, mostly they're all front edges, and the graphs are very sparse. We do not have cross edges like these, and therefore the number of it's pretty much like a cyclic graph, which is control flow graph with occasional back edges which are present, and they're all absorbed in this computation, and that's why it is a very sparse graph, which is related to the number of n as the basic blocks. It is nowhere close to order n square. Its complexity is maybe 4 or 5 maximum times n, and that's why E is equal to maybe at most 4 or 5 times n, and therefore the the total amount of time here taken by this dominator computation is definitely order n in practice. And that's a very efficient algorithm which reuses the dominator computation of the leaf nodes in computing the dominators of the parent nodes. Any questions about this?
Nothing in the chat.
Okay. So so this is the way we will introduce the phi functions. We'll compute the dominator frontiers of each one of the basic blocks through this particular process, and then bind them to all the phi functions which are introduced by the definitions in that block, and usually we'll take their closure and we'll terminate. Now, one of the last things that I want to kind of show here is still this can result in a little bit of unnecessary stuff. How? Let us look at this again, this type of a diagram, and this is the issue of the closure, and that's what we must guard against. Many times, let us say that we have a definition here, A1. So in this particular case, what will happen is we'll have a phi function of A here. This phi function of A will propagate all this stuff here. And in the bottom, I'm drawing another phi function here, and that will again propagate and so on. The reality will be, however, that this A will, some definitions will get generated and they will get used here in this loop region and so on. But there won't be any use of this A, potential any use of A in this particular part. There won't be any use of this A in this part as well. And we'll be generating these particular definitions. Now you can see that what is the problem here? The problem is this, that A is used in only certain parts of the program here, and although theoretically there is some definition, so this definition of A, maybe A3 is used here and in some other parts which is dominating, and but when this merges with that one, that combined definition is not used here. Sometimes it will be used, but some other times it will not be used. So then why keep propagating these phi functions and generation thereof and all kinds of different things? Because this is going to really, first of all, increase the size of IR. Okay, so it will generate the right definitions, no doubt about it. But those definitions, X6, for example, will have absolutely no use in its region of wherever it is active. This X8 here, which is generated, will have absolutely no use. And this will go on and on and on till the whole flow graph. And we'll end up spending a lot of time in generating these definitions, and also perhaps later doing SSA renaming step and things like that. And expand the size of IR will be high, and the amount of time generated in this IR will also become high. So what they do is they restrict generation of phi functions in one of the two ways. The simpler way is this, that they will find out wherever that basic block we are placing this phi function, whether that variable X there, in this particular case, A3, right? Or variable A in particular here, okay, is live or not. If it is not live, that means there is no usage of this variable from this basic block downhill on any. And so therefore there is no need to propagate this phi function generation. So the moment you hit a particular basic block where the variable is not live, you don't need to propagate the generation of that particular fee function because there is no use of it. And the therefore you can prune it substantially. And for well sound, which have of course have definition points before any one of those use points, which the kind of homework that you did in terms of sound, where there are all definitions sitting before any of the uses. This condition will guarantee that we have several regions in which there is no use of this X, and so therefore, of course, no definition which is also theoretically coming to any of these, and therefore we can avoid placement of these fee functions. So in short, when we do this fee function computation in this dominance frontier business, one additional check we do is this variable live here? Or if it is not live, we do not place that, and we don't include it further it in the closure, and that's how we keep the size of IR and other stuff to a minimum. So this is called as pruned SSA, and this is used in practice. So again, what is the step? Everything else remains the same. We find out the dominance frontier for a given definition. But before we do the fee function placement for that particular variable in that block, like in this case over here, we check if this variable is live or not in that block. And if it is not live, we do not place this fee and do not include it in the closure either further. And this gives us a smaller size of SSA, which is better, and we don't have to spend time in propagating this new definition and so on to new places of its merging and so on. Now this itself means that of course we have to do a liveness analysis before this, and we have seen it in our earlier classes that a liveness analysis, which is based on non-SSA form, which if we do, can consume some amount of time. So then there is another alternative which most compiler writers have adopted, is this, that only include in the original analysis unit those variables. So this is an approximation which have definitions in 2 or more blocks. So for example, if a particular unit has many temporary variables, those temporary variables are typically consumed within a block itself and do not get used across blocks. So they will not get included in this analysis or SSA generation. For example, in this block, I will have some A1 and then it's all its uses here and things like that. Now in general SSA related stuff, so forget this one, I have just A1 here. What will happen is this will still insert a fee function here, because of which all this propagation and closures and all will start, and that will lead to the explosion. So in this particular case, if this is the only definition point sitting in the program, we will not actually include this in the SSA generation. So include those which have 2 or more definition points, which are there in 2 or more blocks. Include only those, such as for example A1 and A2. So we'll include this particular case in the SSA generation, but if it were only one, we'll not include that. And that will result in a faster generation of SSA and also a more efficient one. Because obviously if it's one definition, many temporaries, as I said, simply are generated by code generator in a given block, and they get used there and consumed right then and there, and they're not live across blocks. So this is an approximation included based on the number of definitions seen in the IR. So ones which are 2 or more are only included. But of course, that doesn't solve the complete liveness problem. And for that matter, it does eliminate some problem, which is because of some very local temporaries, but it still leaves it on place for non-local temporaries, which may not be live. And those are the ones which are picked up by this full liveness analysis. So what is the modern SSA generation all about? First, we run the liveness analysis. We find out which value is live where, and we stop insertion of gating functions at the first basic block where we find that the value is not live, and therefore its iterative dominance frontier computation is stopped from that point onwards. So that's the thing. And how do we drive the dominance frontier computation? We do it bottom up. Again, dominance frontiers at the leaf nodes are all locals, and then we keep propagating them to the immediate dominator towards the root of the dominator tree. And the overall analysis time here for phi function insertion is order n in terms of the number of basic blocks. So let's stop here, and we'll take up how to fill up these phi functions in the next lecture. And if you have any questions, please talk to me in the office hours. Thank you. And see you there.